the difference here with this part B, it's not a different topic. The difference is that there's more than two variables. The things that we looked at before were, say, area of a circle as a function of the radius, and we did a related rates formula for that, where you had dA dt was 2 pi r times dr dt, where there was only two variables involved at the start. You do end up with sometimes more than two variables involved after, because not only do you have the radius involved here. At the beginning, all you have is radius and this. In the end, you have the rate of change of area, you have the radius itself, and you have the rate of change of radius. Those would be two different things you would have to measure. So if you're having a circle that's expanding, right? If some circle is expanding in size here, sort of, it jumps one at a time. But as you have this circle expanding in size, the rate that the area is increasing at, like if this was an oil spill on the ocean or something like that, that's getting bigger. That's kind of like the area of a circle, radius, right, from the center of the thing. The area is going to be getting bigger based on two things, based on whatever the radius is at that moment and the rate of change of radius. Okay, so when the thing is bigger, an increase in this makes a difference, more of a difference than when it's smaller, right? When you go from a tiny little circle to a slightly bigger circle, you're gaining some area. Think about going from a circle that has a radius of 1 to a circle that has a radius of 2. You go from 1 pi to 4 pi, right? That's the areas. So if it changes from there to there, that's a certain amount of area you gain on there. Maybe it'd be better to think of rings here. There's, let's say, a circle of radius 1. There's a circle of radius 2. You're gaining, if the radius is changing at a steady rate, getting bigger at a steady rate. When you go from 1 centimeter to 2 centimeters, you gain that much. But if you do the same change from 5 centimeters to 6 centimeters, you gain way more area that time, right? Changing a radius when it's bigger, so the radius affects how much area you're gaining per second or whatever, but the rate of change affects it as well. It's not just, some of the formulas you didn't have this in there, and it was just the rate of change of area is related to the rate of change of something else. Okay? I need to actually draw a circle in some other thing that I can show you. I want to look at this one right now because I think it's a good one to try and make some sense of here. So there's a rectangle. This is the formula we came up with. Let's make the rectangle inside the area here. Make that smaller. Oops, that's not good. Okay, you have this rectangle here. We started with the formula area equals length times width, right? The area is the length times the width. Before you start talking about rates of change of things, if I change this, if I make the length smaller, the length is going to be this longer direction here, the horizontal direction, and width is going to be this way, even if I make the rectangle like that. If I change the length of this thing, obviously the area gets smaller, right? You know that from before, area is length times width. If you cut the length in half, the area is half, right? When we write these kind of related rates formulas, we're looking at how fast is the area changing. So we're not just saying you cut the length in half, you get half the area. We're saying if I do it that fast, the rate of change of area is different than if I do it this fast, right? If you change this at 1 centimeter per second, it's different than changing it at 5 centimeters per second, right? When you get a formula like this, it's saying the rate of change of area. When the area is going down like this, leave it there. When the area is going down like this, you have a negative rate of change of area. In this situation that I'm doing right now, what's the rate of change of the width, would you guess there? One little notch in this grid, whatever, it's kind of snapping to a grid here. 1 notch per second, maybe? Whatever unit that is. Like on the screen, it's obviously bigger than on my screen here. But it's 1 of those per second, right? That might be the rate of change of width. of this dimension. If I'm losing one little notch on this grid every second, it's one space that way times whatever this dimension is. That's how much I'm losing every second, right? Over here? Not really, because these are, it depends on what you want in the situation. If you wanted to measure this, you could probably write a related formula that involves that. But likely what you want is the two dimensions. Let's make up some numbers for this. Let's say that this was, at one particular moment, let's say this is 20 centimeters here, and this is 10 centimeters. And let's say that this is decreasing this way at minus 1 centimeter per second. And let's say I'm not changing this direction. I'm only shortening it the other way, right? So I'm only doing this. I'm shortening it this way. I'm not shortening it the other way. So what's the other rate here? The other rate is 0, right? So it means that this way is 0 centimeters per second. I'm not changing that at all. So then if you want to know how fast the area is changing, you could plug in all the numbers, but just make some sense of what's happening here. So this, I was calling this the length. So the rate of change of length is minus 1 centimeter per second. And we're multiplying that by the width at any given time, right? The width is, this way is 10 centimeters. Plus the other thing is, it doesn't even matter how many centimeters because this is 0, right? It's out of the screen. We cannot fix that. Well, whatever. Too complicated. Exactly. I think we can not worry about it. There. So all of this part disappears, right? Because this rate is 0 here. This would give you, what would that simplify to there? Negative 1 centimeter per second times 10 centimeters at any one given moment here is negative 10 centimeters squared per second. Now, in this situation, this dimension doesn't change, so we can look at what happens all the time here. If I'm changing this at this rate, if I'm changing the length, I'm making the length smaller at 1 centimeter per second. Every second I'm losing 10 centimeters of area. That's what you're saying, right? So after 1 second I lose that much. That's 10 centimeters squared of area. I lose another. Like I'm losing a strip off the edge here every second. Right? This little strip here and another little strip. I keep losing that every second. You're multiplying the width by how fast you're changing it. It makes sense, right? However wide this is, times however fast you're shortening it, that's how much you're losing. If this was changing, or this was not a rectangle, like this was some irregular shape here, it might still be involved like that, but this would change. If I was changing it like this, where I was changing both of them at once, like if I'm changing it like this, then at any given moment, this is going to be different, right? So you need to know what this is at any given moment. You could say, like, at this particular moment, what's the width and what's the rate of change of length? And we'd need to involve this because neither one of them is 0 at that point. It would be based on 4 things. This would be a complicated thing to look at because it would be based on 4 different things. It would be based on how fast it's changing this way, how fast it's changing this way, and what the actual dimensions are at any given moment. You could sub those 4 values in and get how fast the area is changing. You could make it where one of them's increasing and one's decreasing. Like there, the length is decreasing, the width is increasing. So you could stop at any given moment and find out how fast is it changing. That's what these formulas are. That's what you're generating here when you generate one of these formulas. Okay, you should look at each of these as a separate variable. That's a variable you could measure. That's a variable you could measure. And the other ones are as well, right? That is, and that is, right? All 4 of those are different variables in a particular situation. This is bothering you that that's a different color? Oh, yeah, whatever. That's not 10 minutes, panic, it's 10 minutes, okay. So when you work through this, just hang on. Some people are good when they're given a formula to start with, because they say, oh good, I differentiate both sides to come up with something. You do sometimes have to make up your own formula for whatever the situation happens to be. And you have to think about whether certain things are variables or constants, as you have run into already. You have done some of these things. We'll stop this.